Some basics. We had Newton's laws. Newton's first law, often called the law of inertia, said the only way that you can accelerate if there is an unbalanced blank acting on you. What word would go in the blank? What must Sorry? Yeah, if you're accelerating, you know the forces are not balanced. If you're not accelerating, now remember, not accelerating can happen in two ways. You can be at rest, you're not accelerating, or you can be going in a straight line at a steady speed. That law explained how outer space works, which is one of the reasons we hold Isaac Newton in such high esteem. In the late 1500s, he was already anticipating and predicting how outer space would work if we got there. In outer space, if you fire your rocket and then shut your rocket off, you're going to keep going in a straight line at a steady speed. You don't bank and curve like Star Wars suggests. Star Wars, the spaceships fly like airplanes. They shouldn't fly like that in outer space. Anyways, that's another rant. Newton's second law was the equation. I often say it as F equals what? Really, what I should say is F net equals ma. And what do we mean by F net? The combined sum of all the forces from our free body diagram. But that gave us a bit of a trigger phrase. Anytime you saw the phrase net force, you could skip the free body diagram and go straight to ma. Newton's third is often phrased as, for every action there is an equal and opposite reaction. I typically say forces come in, and I'm going to change that next year. I'm going to say forces come in opposite pairs, and that emphasizes that they're pointing in opposite directions. So I will mention that. You ready to go? Because I'm just watching you turn. You got the calculator, got the formula sheet? Okay, here we go. A net force acts on a 6 kilogram mass and gives it an acceleration of 3 meters per second. How big is the force? How can I figure that out? F equals what? As far as I'm concerned, I can give you any two of these and find the third, and I would consider that a C- level question in forces. If I give you any two of mass or acceleration or force, you can find the third thing. In fact, this one I can do in my head. 18 newtons, yes? Okay. There's going to be an elevator question on your test. An elevator question was one of the first times we started using a free body diagram. There will be a question on your test where I just give you a situation in a word problem, and then I give you 4 free body diagrams to pick from, and I say which of these is the correct free body diagram. That's probably how I'll test, can you draw a free body diagram? A 900 Newton person, wait a minute, that's newtons, not kilograms. What did I give you when I said a 900 Newton person? What did I give you there? I gave you mg. What's another word for mg? No now. What? No now. What? Wait, no now. So I gave you this here is weight, which is the same thing as mg, the obvious one. I might give you their mass in kilograms, but I have no problem giving you an object's weight in newtons, because how would I change that to kilograms if I needed m? Divide by 9.8. I might leave it like that. We'll see. Anyhow, stands on a scale on the floor of an elevator. What's the scale reading for the elevator if the elevator has an acceleration? What's the scale reading for the person if the elevator has an acceleration of 3.6 meters per second squared up? This is a job for a free body diagram. We represented the person with a dot. What were the forces acting on this person? Get the obvious one. Why do I do it that way? I'm trying to teach you. Worry about the bizarre, uncertain forces later. Often, if you do the basic ones that you know, the other ones will fall into place. So I always do gravity first. And then I say, what else? Shouldn't I put scale? Say no. Because although this question is asking me to find the scale reading, what's that a synonym for? What does a scale actually measure? It doesn't measure mass. It doesn't measure weight. I had somebody stand on the scale and do deep knee bends, and we noticed that the scale kept changing, but their mass and their weight weren't changing. And we thought about it for a while, and somebody had that aha moment and realized, yeah, the scale reads the normal force. And so when I'm asking you to find the scale reading, you'll tell me the normal force. Normal force pointing which way? Bigger, smaller, or the same size as mg? And how do I know? How do I know bigger? I can't be fussy. Not because it's going up. I need a word that starts with the letter A. It's accelerating up. If it was moving up at a constant speed, in fact, if it was moving up and slowing down, okay, all of those are situations where it's going up, but I'm telling you the normal force would not be bigger than mg, so we're going to be fussy in our language. And I told you in my free body diagrams, I always exaggerate it to make it kind of Captain Obvious. So then we had this tug of war analogy. What we used was this idea of winner minus loser equals the net force. And what I really meant was the winner is the direction of the acceleration, the loser is in the opposite direction of the acceleration. We no longer let up be positive and down be negative. We let positive be whatever made the math nice. Who's winning? Who's losing? What's that equal? How can I find the normal force? How would I get the Fn by itself? So it's going to be mg plus ma or ma plus mg. It's going to be mg is 900 plus m is not 900. M is 900 divided by 9.8. And I'm lazy. I'll just write that times a. What's the acceleration here? Can all of you crunch that on your calculator? What would this scale read in newtons? I think the answer is going to be bigger than 900. 1,231? Anybody else? So if this was multiple choice, I might write it as 1,200 if I went to 2 sig figs, or 1,230 newtons. What if I, as just to make it one level more difficult, said the scale reads kilograms? How would I change that to its equivalent scale reading in kilograms? How do I change newtons and convert it back to kilograms? Could you do that on your calculator? Sorry? So this person would feel as though they had a mass of 126 kilograms. I could figure out their original mass by going 900 divided by 9.8. I'll tell you what it is. It's going to be really close to 90 because that's almost 900 divided by 10. So their original mass is right around 90. They now feel like they weigh 125 kilograms. This is what any amusement park ride does. I think I showed you the video of the kids' first roller coaster ride, and we said any good amusement park ride, it can't change gravity, it can't change your mass. What they can change is the normal force, and it turns out we'll pay money for that. B. Here's my free body diagram. What are the forces acting on it? Get the obvious one. What else? Smaller, bigger, or the same size as mg? What's my equation going to be here? How would I get the Fn by itself? In fact, we gave this a silly name. We called this the swappy dance. I've been told by Mr. Gerard that the grade 12s have started using that term, and so he's going to start to use that term in his math classes as well when you're solving just that and just want to swap the two things. He likes that, so we'll reinforce that. I can't claim credit for that silly term. Mitra Timiori, who graduated 3 years ago or 4 years ago, she made that term up and I stole it from her. So when we have a minus here and this is still positive, they basically switch places because you minus this over, which would tuck it right there, and you plus this over, which would tuck it right there. You get normal force equals mg plus ma. So it's going to be 900 plus m is 900 divided by 9.8 times a. Mr. Dueck, doesn't a need to be negative because it's going down? Doesn't the 4.3 need to be negative? I took care of that in my winner minus loser by who I let be the winner, so I can avoid the negative 9.8s in this unit. In free fall, absolutely down was negative and up was positive because that was always in the same directional reference frame. What do you got? Wait a minute, Mr. Dueck. Minus, Mr. I did this wrong, didn't I? It would be mg minus ma. Minus ma, Mr. Dueck. Minus ma. Wow. Would you have plus as an answer? Probably. So don't do what I just did sloppily. It's going to be less than 900. What'd you get? 505? Could you divide that by 9.8? How many kilograms, when this is accelerating down, would this person feel like their mass was? Loud and proud, sorry? 51.5. So if you've been on the elevator, for example, On the way down, you feel lighter. There's actually still plenty of force holding you in the chair. I think those shoulder restraints, if they vanished, as long as you didn't push yourself off in a panic, I think if you had your feet and hands up like this, you'd still stay on the elevator. You just feel like you're going to fly off because you're not used to feeling lighter than normal. All of you have had experiences growing up where you feel heavier than normal. For example, when you give somebody a piggyback. When someone dog piles on you. At the bottom of a swing, if you do the free body diagram for that, I assure you, you'll feel heavier than normal. You have plenty of childhood experiences where that is the case. The only time as a child that you feel lighter than normal is when you're in free fall on a trampoline, jumping up and down, or off of a high dive. And you might notice jumping off of a high dive or a diving board not everyone can do it. It's a pretty intense experience. What's the answer to C? What if the elevator is accelerating at 9.8 meters per second squared down? What would the normal force be? What would the scale read? Huh? 0. This person would feel weightless. Are they weightless? No, they still have a weight of 900 newtons, and that's why we call free fall apparent weightlessness. Gravity is still acting on you. In fact, I think I showed you the OK Go video where they were diving down in an airplane and removing the normal force, and it looked like there was no gravity. There was, but when there's no normal force, things appear to float to us. And I think we agreed that that's what the astronauts are experiencing in the International Space Station. They're in continuous free fall because gravity reaches up to the International Space Station. They're in continuous free fall, and that's why they have no normal force, and that's why they float. So Fn would be 0. You're going to have an Atwood machine. It says find the acceleration and the tension if M1 equals 18 kilograms and M2 equals 21 kilograms. So I'm going to write here 18. I'm going to write here 21. How did we handle this? Free body diagram. What are the forces? In fact, we got a bit sloppy. Rather than doing a separate free body diagram, we actually labeled the diagram if they gave it to us because we were naturally lazy. What are the forces acting on M1? Get the obvious one. Is there more than one mass? I'll call it M1G. What else? Tension. What are the forces acting on M2? M2G. And? Is there a normal force? Only if you're sitting on a surface. If you're not sitting on a surface, there is no normal force. So for there to be a normal force, I would have to have like a table or something right there. I will actually do an example like that in Physics 12, and you'll find it's a really easy tweak. You get one more winner or one more loser in your equation, and okay, big deal. Anyhow, who's winning? Now we had to just use our brain. Which one of these masses is going to be the one that's accelerating downwards? Who's winning? Sorry? So we're going to have that be the winner. Anything that ends up pointing down on this side is going to be winner plus. Anything that ends up pointing up on this side is going to be loser minus. And so we're going to end up with M2G, and then we're going to have a minus tension. We're going to have a plus tension minus M1G. When we had more than one mass on the left-hand side, what was the only adjustment we had to make on the right-hand side? It was going to be M all times A. If you get to this question, you are allowed to put your pencil down during the exam. And you can stretch. Why am I so relaxed, folks? Oh, I'm losing tension. Always like that. And so to get the A by itself, I would divide by M all. And it's going to be M2G minus M1G. Try going straight to your calculator now. You're going to have brackets around the top, and you're going to have brackets around the bottom. There is a built-in error check for this question. If I cut the rope, what's the maximum the acceleration could be? And so it's going to be less than 9.8. In fact, I can make a better prediction. I'll bet you're going to get an answer less than 3, probably less than 2. And the reason is these masses are nearly identical. It's probably accelerating really slowly because 21 and 18 are so close to each other that there's only a 3 kilogram difference. That's not going to have a big acceleration. As opposed to Antonio, if this was 18 and 210 kilograms, then I would say the acceleration is going to be pretty close, 9.8. Am I right? Is it less than 2? Certainly less than 3. Less than 2? Less than 1? 0.3 sig figs. 0.753? 0.754 meters per second squared. Okay. So, and the reason I mentioned that little trick is if I was pressed for time or running out of time, I might be able to eliminate some wrong answers on the multiple choice just by looking at how different the masses are and deciding, hey, is this going to be a big acceleration or a small acceleration? Oh, he's got an answer bigger than 9.8. Nice try, Mr. Dueck. Oh, that was the acceleration. Why can't I use this equation here to find the tension? Because I have a tension deficit disorder. Because the tension's crossed out. Some of you are like, yeah, I can relate. Okay. So to find tension, we just looked at one mass. Didn't matter which one, although often one was easier, but it really didn't matter which mass you picked. Which mass would I pick? Or let me say it this way. Why, if I was really clever, would I pick mass 1 and not mass 2, even though they'll both give me the same answer? Tension's the winner here, and it's going to be easier to get the t by itself. And how do I know tension's the winner here? Because it's accelerating up. In other words, I would go tension minus m1g equals m1a. And do you see how it's easy to get the t by itself? If I did this one, I'd have to do the swappy dance. Although I'm doing that in my head anyway, so it's really not that big an issue. Plus the mg over to that side. So you still have the a on your calculator. Can you go 18 times answer button plus 18 times 9.8? What's the tension? What do you get? Anybody else? 190, 190, 190. Okay. So there's going to be an Atwood machine on your test, and I'll either ask you to find the acceleration or the tension, or I could maybe do both and have like a little 2 columns, A acceleration, B tension, or something like that. What I won't ask you to do is find a missing mass. We did it in this unit where I gave you either the acceleration or the tension, and I didn't give you one of the masses, and we worked the whole way backwards to find out what the missing mass had to be. Not on your final, and I think I crossed those out on your review anyways, so I think we're good. Suppose a force of 130 newtons is required to start a 12-kilogram box moving across a concrete floor with a constant velocity. You know what? That phrase, constant velocity, is an important one. What's the coefficient of friction between the floor and the box? What's this question asking me to find when it says, what's the coefficient of friction? Which variable are we talking about here? Hey, what's mu? I don't know what's mu with you. How would I solve this? What's the first thing that I would do? I would do a free body diagram. So I'm imagining the box. There it is. What are the forces acting on this box? Get the obvious one. Is it sinking into the ground like quicksand? Is it flying here like Superman? So we can argue that there's a normal force the same size as mg. What else? How big is the applied force? 130. What else? Bigger, smaller, or the same size as the applied force? How do I know it's the same size? Okay. If it was slowing down, friction's bigger. If it's speeding up, friction is, yeah. That's Newton's first. Okay. That's, I think I would have said many times, Newton's first, very powerful law if you think about it. It really helps you with your free body diagrams. But you're right. Here I know they're the same. So normally I could go who's winning, who's losing. But you know what? It's a tie. I could jump straight to saying F applied equals friction. 130 equals friction is what times what? I don't know the normal force. Oh, but look, 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 look. I don't know the force the same size as the normal force. Which force is the same size as the normal force? Will that always be the case? Sure, no. When won't that be the case? If there are extra vertical forces. What do you mean? Stuff like this. And there is going to be at least one of those on your test. 2. We'll get to that. But for now, we can say 130 equals mu mg. How would I get the mu by itself? Divide by mg. So on your calculator, can you go 130 divided by 12 times 9.8? What's mu? I don't know. What's mu with you? Ooh, did I make up bad numbers? Sorry if I did. 1.1? That's a really big coefficient of friction. I was making up bad numbers. Usually I like them to be between 0 and 1, although they can be bigger than 1. This doesn't happen very often. This is a really, really sticky floor. Okay. Consider the following diagram. Suppose the applied force here is 160 newtons. Supposing that mass 1 is 12 kilograms and that mu is 0.6, find the acceleration. Okay. What would I do here first? Yeah, but you know what, Court? Since they gave me the picture, I'm going to draw right on the picture, if that's okay. What are the forces acting on this? Get the obvious one. What else? Bigger, smaller, or the same size as mg? I don't see any extra vertical forces, so same size. What else? Well, we have the F applied. I'll put an arrow on there just so it catches my attention. And they even told me how big that is, so I'll write it on the picture. It's 160 newtons. What else? Bigger, smaller, or the same size as mg? I think smaller, so I'm going to guess friction is losing. If I get a negative acceleration, that will tell me, uh-oh, friction's the winner, and I have to redo this really quickly and make every loser a winner and every winner a loser. But it's an easy fix. For now, who's winning? Who's losing? What's that equal? MA? I'm going to do that. A is going to be 160 minus, and then we would say friction is what times what? And all of you would say mu times the, and then I would say, I don't know the normal force. Oh, but look. And you would all say, so I'm just going to go mu mg all over m. So try that. 160, m is 12, mu is 0.6, g is 9.8. I'm hoping we get a decent answer this time because that last 1.1 means I made a bad one. Uh, 12 times 10 is 120.6. It's going to be that. It's going to be roughly 80 divided by 12. Very roughly, it's going to be 40 divided by 6, 20 over. Are you getting something in the 5 range? Boy, I could be way off. What'd you get? 7.45. Oh, I should have gone higher. I went lower instead to compensate. You're right. I should have gone higher than 6. Sorry? 7.45. 7.45? I knew I had to compensate, but I compensated in the wrong direction. My rough math, I got 6, and I said, yeah, but I think I'm too big. No, it's too small. Dumb. Okay. Is that okay? Now, if I wanted to make this nastier, instead of saying find the acceleration, I could say assume this object starts at rest. After traveling for 20 meters, what's V final? And so even though the question is asking for V final, you know what you'd spend most of your time finding? Acceleration. And then once you had A, you could use VF squared equals VI squared. In other words, once you have A, as far as I'm concerned, if I want to make a nastier question, all of the kinematic stuff is now in fair play. Okay? This block below is accelerating downwards at 2 meters per second squared. What's the tension in the rope attached to it? How would I solve this? And since they gave me a picture, you know what? Actually, I'll do a separate free body diagram just to make a point. So what are the forces acting on this? Get the obvious one. Phone's away, right, Logan? Completely away, right? Okay. Gravity. What else? Well, there's a rope. Yeah, what do we call that one? Is tension going to be bigger, smaller, or the same size as mg? I've heard smaller, I've heard bigger. The good news, one of them is right because it's not the same size. How do you know smaller? Rowan, which way are we accelerating? So which way must the winning bigger force be pointing? So tension's going to be, yep. This is an old trick. If you're ever dealing with a really ratty rope and you're worried it might break, as long as you keep whatever you're lowering accelerating downwards, you can lower tension. Now the problem is that means as you're lowering it, that object's going to be speeding up and speeding up and speeding up and speeding up and speeding up, and you don't want to have it hit the ground and smash. So eventually you're going to have to somehow bring it to a stop. But it's an old trick if you need to in a pinch. What's my equation? Get the T by itself. It's Swappy dance, yes? And now, the fact that I heard somebody did it wrong verbally, I always, if I can, draw those arrows almost always, I'll write it the right way. Mr. Dueck, you forgot the negative a few minutes ago. Shut up. I'll almost always write it the right way. I didn't put the arrows in on that swappy dance, and I should have. That would have caught it then, because then I'll drop the negative down properly. What'd you get? Can you go 4 times 9.8 minus 4 times 2? 28 plus 3.2, 31.2? I can still do math in my head. What if we had the same question, but now we're accelerating upwards? This is a job for a free body diagram. Gravity. Rowan, will tension be bigger, smaller, or the same size as mg in this question? Why? What if we were, I gotta be fussy, not because it's moving upwards. I need a word that starts with letter A. What if we were moving upwards at a constant speed? Yes, so you see why I'm being so fussy? But that's key, and that would also be a good multiple choice question to throw at you. Anyways, so here my equation is going to be tension minus mg equals ma. Tension is going to be ma plus mg, which is what? Do that one in your head, Mr. Dueck. Well, it'll be 11.8 times 4, so it's going to be 44 plus 3.2, 47.2. Still got it. A couple more and we're done. Find the maximum force of friction. So let's assume we're pulling this to the right and friction is resisting us. What's the biggest friction can be? Why did I say maximum? Remember, we said friction is only going to be as big as it needs to be. I walked over to the poor people that were sitting in this desk right here, and I pulled with 2 newtons, and we said friction was 2 newtons. And I pulled with 3 newtons, and we said friction had to be 3 newtons because the forces clearly are balanced. But there's a maximum that friction can be. He's pushing down really, really hard. Well played. I saw you doing that because the front part moved, but this part didn't move. Well played. By the way, why were you able to increase friction? What force did you increase by pushing down? Darn right you did. That's why friction is not equal to mu mg. It's got to be equal to mu times the normal force, because that lets him pull that stunt. Well played. First time a kid has ever done that while I've done that demonstration. I hope there's more, because that was a good teachable moment. So we're finding the maximum force of friction. We would say this, well, friction is mu times the normal force. But I'm not going to say, I don't know the normal force. Oh, but look, because the normal force is not mg. There's an extra vertical. There, we got Jagger pushing down. So, this is a job for a free body diagram. What are the forces acting on this? Get the obvious one. I have mg. I have some horizontal. I don't care about that right now. I want to think about the normal force. Is the normal force going to be bigger, smaller, or the same size as mg? The good news is one of those is right. It's not the same size. Let's think about it. You know what? Let's just do it wrong. What if we said smaller? Okay? It's not. It is going to be bigger. But what if we even wrote it that way? We're still okay because, ready, Courtney? Is this sinking into the ground like quicksand? Is it flying to you like Superman? So everything down has to equal everything. What's the only force pointing up? So we would write everything up has to equal, what are the 2 forces pointing down? And now you might say, oh, we're adding 19 to mg. The normal force is bigger. You might even catch it there, even if your arrow was wrong. Hopefully you would still get the right magnitude, okay? Can you crunch that on your calculator, and then can you go multiply that by mu after hitting equals? So it's going to be 0.58 times 3 times 9.8 plus 19. How big is the maximum force of friction? Sorry? 28.1? I'm seeing people shaking their head. Yes? Yeah, 28.1 newtons. Only because of Jagger. Well played. Well, what if instead of pushing down, we lift it up? Oh, and what if we said, let's find the whole acceleration? This is our final question. This is about as tough as I can throw at you with a single mass. Okay. Free body diagram, although since they gave me a picture, let's label the picture. What are the forces acting on this? Get the obvious one. There's this 13 newtons already there. That's not the normal force. This time Jagger is lifting up. He's hoping that when I tug, it will feel so light that I'll fall backwards and make a fool of myself. Well played, I say again. Well played. So he's lifting up. So there is still going to be a normal force, but this time the normal force is going to be smaller. In fact, these two are what's canceling out gravity. I'll come back to that. We also have F applied, and we have friction. Who's winning? Who's losing? What's that going to equal? MA. Now, I'm guessing F applied is winning. If I get a negative acceleration, then I'll know that friction is winning, and I'll have to redo the question and make my winners losers. I might have to move a couple arrows around, but it's a pretty easy fix. Friction is what times what? I don't know the normal force, and I can't say, oh, but look. So I'm going to do the normal force right here. Is it sinking into the ground like quicksand? Is it flying to like Superman? That means all the forces down have to equal all the forces up. Or all the forces up, which is the normal force, plus 13 has to equal all the forces down. How would I get the normal force by itself? This time the normal force is going to be mg minus 13. And if you wanted to, you could crunch that. I'm going to see if we can do this all in one line, Antonio. So I'm going to walk over with this, and I'm going to write F applied, which is 41, minus mu bracket mg minus 13 equals the acceleration divided by m to get the a by itself. So on my calculator, you can try this if you want to do this in one fell swoop with me. We can go like this. Bracket 41 minus 0.31 times bracket 9.6 times 9.8 minus 13. I have to close off the mg minus 13 bracket. I also have to close off the top divided by... Do I need to put the bottom in brackets? Only one term, so I can get away without it. 9.6. And I get, I hope, an answer. 1.65 meters per second squared. So that's a really quick review of the fundamentals of forces and some of the advanced stuff of forces. That's going to be around 10 questions out of 36. So that basically makes it that around 25% of your final exam. In other words, if you were walking through all this going, oh, I'm going to ace this, then you can walk into the exam with some good confidence on that section and say, hey, I just need to make sure I don't make sloppy mistakes like Mr. Dueck did when he forgot to bring across a negative or something dumb like that. Okay? The remainder of class, 25 minutes, is yours, my angels.